Bismillahirrahmanirrahim. So in today's lecture, I am going to teach you the calculation of average crystallite size by Williamson-Hall equation. And this is again a very important equation, and the importance of the X-ray data or the pattern to use for the calculation of the average crystallite size. And again, this is important for the nanomaterials because we are going to use this technique and the equation to calculate the average crystallite size. So remember in the previous video, which is the link is given over here, we have discussed the crystallite size by using the Schiller equation. And now this equation is particularly for the average crystallite size, because here we are going to consider all the peaks at the 2 theta degrees. So first have a look at the equation. This is actually the three forms of the equation, and there is again no difference between all these three forms. Let's understand the first one. This is the beta cos theta, and 4e is the epsilon sine theta k lambda over d, and d is the crystallite size, k is the shape factor, and it is constant bearing the value of 0.98. And this is for basically for the spherical shaped particle. And lambda is the wavelength of the X-ray source being used for the diffraction data, and its value is 0.154 nanometer or in angstrom. Again, beta is the full width at half maximum of the peak at all the peaks in the XRD, and at particular angle, which is in theta in degree, but we will convert into the radians. And this I have already explained in detail, how to find out the full width at half maximum and how to convert the degree into the radians. And please watch this video again if you need any help for this type of the understanding or the conversion. Again, this theta is the Bragg's angle of the corresponding peak at specific Miller indices that mean at specific HKL values, and this should also be in radians. And this epsilon is the crystallite size. So these all of the parameter I have explained over here. So now look at this equation. This is the equation having the straight line equation with the intercept. This is the straight line equation, y equal to mx plus c. And you remember there are the two forms of the straight line equation. One is the with intercept here plus c, and the other one is without intercept, that is the y equal to mx. But this equation is with the intercept because the plus sign is here. So beta cos theta equal to this one. So this whole will be the y, and for e sine theta, it depends. If you take sine theta on the x-axis, then the slope will be the 4e. That will remain the constant for the strain will be the same for a specific crystallite pattern or the size. And k again, it is have been explained over here, lambda and the d, and this we are going to calculate, that is the crystallite size, by using this equation. That means this is the x, and this would be the m, and k lambda over d would be the intercept, and these two are the constant. So the intercept will be equal to k lambda over d, or d will be equal to k lambda over the intercept. So actually you are going to get the value of the intercept out of the graph, and then we will use over here to calculate the crystallite size, and that would be the average crystallite size, because here we are considering all the theta values. This is another form of this equation. Just what is the difference over here? I am just going to divide this equation by the lambda. So this would be the beta cos theta over lambda, 4e sine theta over lambda, and lambda divided by lambda is cancelled out. And this you may also plot by the graph by using this equation. Again, there will be no change in the final answer. And here the y would be equal to beta cos theta over lambda, and for e would be the m, and here x would be the sine theta over lambda, and the intercept would be the k over d. So with the intercept, you will directly calculate the value of the d, which would be the d will be equal to k over c mean intercept. This is another form. And here, what is the difference between this and this? I am just because 4 is the constant, you may take with the slope, and also you may take with the x. So this is just the rearrangement of this equation. 4 is here. All the equation is the same as I have discussed over here. Again, there should not be any difference in the final answer, that is the crystallite size. So now I'm going to use the data to calculate the average crystallite size by Williamson-Hall equation. This is the data of the XRD pattern of these two metal oxides, cerium oxide and the zinc oxide. And again, this is our own paper, it is published, and you may further, if you want to get more information about the XRD or the other important calculations, you may visit this paper over here. So here 2 theta, here actually we are considering 2 theta because this is the X-ray source. It is going to, when it is going to fall on this sample, it is diffracted. The angle is the theta, it may be any angle. And when it is diffracted, if you take the angle from the incident X-rays, so it would be the 2 theta, double to this one, because for the constructive interferences, this should be equal to this. So for the diffraction angle should be half of the 2 theta. Actually, this we are going to consider for the calculation of the crystallite size, but the instrument is going to give you the 2 theta value. So that is the reason why we are going to convert the 2 theta into the theta values. Now I am going to show the Excel file over here, and let's see very simple calculation as we have discussed before in case of the Schiller equation. So these are the HKL values as these were indicated in the XRD pattern in the previous figure, and these are the 2 theta positions, and these are in the degrees. So now I am going to convert or moving towards the final equation, any one of the final equation to get the results of the average crystallite size. So again, the first step is you have to convert this 2 theta degrees to the theta, and this you can do by just dividing with the 2, that will convert the 2 theta into the theta degrees. Again, important conversion is you have to use the theta in radians, and I have described detailed reason why we are using the radians in the previous lecture. So here, how can you convert? You can even use this Excel by using this function. You can convert all these values from theta to the radians, or you may use the simple conversion factor which we have discussed between the theta and the degrees. Again, this is the beta. Beta is the full width at half maximum. It will be in degrees as I have explained before, and you have to convert into the radians by using the same conversion factor. By using, you may use this function, or this is the conversion factor which is shown over here, 0.017453. You have to multiply this with the degree to convert into the radians. Now step by step, because our focus is the beta cos theta over lambda, and you first calculate the cos theta. Again, you may use this function to use the to convert the theta in radians to the by taking the cos theta, and now you are just multiplying the cos theta with the beta. The value will give you this. I am just explaining triple one, and similarly you can just move over here, or you may individually calculate the same calculation with the rest of the HKL values. And then beta cos theta over lambda, and the lambda is the constant, that is the 0.154 nanometer. So I'm using nano in nanometer because you will get directly the size in the nanometer. Again, it is up to your choice. For the this we have done with the actually the y-axis. Now the x-axis may be the sine theta, or the sine theta over lambda, or 4 sine theta over lambda. So you may use any one of the x-axis over here. So you know you will take the sine of the all these theta values, and then if you want to take 4 sine theta on the x-axis, you have to multiply by the 4, and of course then it would be the sine theta over lambda if your target is any of the equation like this. And now I'm going to use, because you have already calculated the x-axis and the y-axis over here, so I'm taking just as a reference. These values are given over here. These are the value x-axis, and these are the y-axis, x and the y-axis over here. So I'm just taking as a simple, you may take all these values to plot a graph is plotted over here, just to show you the formula over here. You can take the scattered data, and just for the simplicity you may remove this one, and after this you must go to the add trend line, and then because this is the intercept, this equation is having the intercept. When you close it, you will directly get the answer over here. This is the uh, y equal to minus 0.02 x plus 0.183, that is the intercept, and this is again I have already plotted over here, so I'm just going to delete one of the graph over here. So you will directly get the value of the intercept from this graph, and this is the value of the intercept, 0.183. And then what would be the value of the d, because we have plotted over here the sine theta over lambda, and beta cos theta over lambda, sine theta over lambda, then your intercept is k over d, and this is the intercept, and the crystallite size would be the k over c. C is the intercept, and this is just the, you have to divide the k value. K is 0.98, that is the source, it is the shape factor and constant for a particular uh, crystallite shape, and this is, we are taking 0.98 for the spherical shape, and you have to divide with the c. C is 0.183. This is the O4. O4 is 0.183. That will give you the final answer of 5.35519 nanometer. So the crystallite size of this graph is like it is shown over here. The crystallite size by using the this data is 5 point something. So in this way you can get the value of the average crystallite size by using the Williamson-Hall equation. So this is all about our today lecture.